Good evening and welcome everybody. This is really a great turnout. I don't remember having seen this lecture theatre so full. My name is Martijn de Sterke. I'm a professor in the School of Physics here at the University of Sydney. Before we start tonight's proceedings, I would like to acknowledge and pay respect to the traditional owners of the land on which we meet, the Gadigal people of the Eora Nation, and it's upon their ancestral land that this university has been built. As we share our knowledge, teaching, learning, and research practices within this university, may we also pay respects to the knowledge embedded forever within the Aboriginal custodianship of country. So the name associated with tonight's event is Dr. Peter Domachuk, and there are two things on the agenda. The first is the awarding of the Peter Domachuk Scholarship, which we will do in a minute, and then the second is the public lecture by Dr. Marshall Perrin. But let me tell you a few things about Peter Domachuk first, though. He was an undergraduate student at this university, and after completing his degree, he joined a research group of my colleague, Professor Ben Eggleton, as a PhD student. And Professor Eggleton notes that Peter, through hard work, perseverance, and his confident, highly energized approach, was a highly successful PhD student. After finishing his PhD, he took a position in Boston, in the US, in the emerging field of biophotonics. And here he was part of several groundbreaking demonstrations of silk photonics, which is bringing implantable, biocompatible optical components closer. He returned to Sydney in 2009 on a prestigious fellowship and established new research programs, new labs, and linkages around Australia, but it was during this time that he tragically passed away in early 2013 at age 33. Professor Eggleton further said that Peter was a unique character, and yes, he was, highly intelligent with a dynamic and energetic personality, equally at home discussing the philosophy of science or being a bouncer at Sydney's toughest night joints. Behind his brash personality, though, Peter was a really lovely young man with a love of life. His friend Steve Manos, who I think is in the audience tonight, told me that Pete, as we say with a smirk, look at the smirk, said somewhere between mad genius with a thread of belligerence. Yes, indeed. He had a talent for science investigation and for storytelling, always able to communicate complex ideas in digestible form. And those traits and imagination and knowledge that came with them went beyond the lab and into other interests such as music, food, and the world at large. So Peter's family have bequeathed funding for a PhD scholarship. And this year's recipient is Stephanie Rossini Bryson. And awarding the scholarship tonight will be Miss Katrina Drake, representing the Peter Domachuk family. Can you please come up? And while they do so, yes. Great, thank you. Stephanie tells me that her PhD research aims to build an instrument called GLINT, which utilizes interferometry for direct imaging of exoplanets. The spectra of these images will characterize planets and may ultimately reveal potential signatures of extraterrestrial life. Okay, now then the Peter Domachuk lecture. This lecture has also been made possible by the generous donation of Peter's family. The lecture series is hosted by the University of Sydney, the Faculty of Science, and the School of Physics, and they commemorate Peter's life and his contributions to the university. They support the sharing of information from world-leading optical physicists, like our speaker tonight, with students, researchers, and with the general public. It's an activity of IPOS, the Institute for Photonics and Optical Science, the umbrella organization of all optics researchers at the University of Sydney. So our speaker tonight is, as I mentioned, Dr. Marshall Perrin. He's an astronomer at the Space Telescope Science Institute in Baltimore in the US, where he leads efforts using advanced space optical systems to image and study nearby planetary systems. He served as deputy telescope scientist for the James Webb Space Telescope and co-led the team that aligned its mirrors in flight. You'll hear about that tonight, no doubt. Marshall received his PhD from the University of California in Berkeley in 2006, working on large ground-based telescopes, and subsequently at the University of California in Los Angeles, he helped develop the Gemini Planet Imager instrument. He joined the James Webb Space Telescope team in 2010, where he now leads efforts to develop novel imaging technologies for future missions. He was awarded NASA's Exceptional Public Achievement Medal in 2022 for his scientific leadership contribution to the James Webb Space Telescope. And with that, I would like to ask Marshall to come to the podium and give his presentation entitled Opening a New Eye to Ancient Light, the Optical Advances of the James Webb Space Telescope. Thanks, Marshall.
Thank you so much. All right, well, it is a great pleasure to be here tonight, and I want to begin by thanking Peter's family and thanking the university for the kind invitation and for hosting me so far, and I'm here all week and looking forward to many more good discussions over the days ahead. There's a lot of work that goes on here in photonics, in nanosciences, optical work at the very smallest scales, and I'll be here speaking on the other end of the spectrum, some of the largest optical systems, one of the largest in space now, and what it is to build and to operate at the very largest scales of science. So large teams as well as large systems. We'll be speaking on the optical advances that led to JWST, which has now been operating in space for not quite 2 years. It will be 2 years Christmas Day. I am, as it was said, at the Space Telescope Science Institute in Maryland. We operate Hubble and now operate JWST on behalf of NASA, the European and the Canadian space agencies. And on behalf of the world, really. And so I want to really emphasize that the work I'll be speaking through tonight is on behalf of many thousands of, literally thousands of people contributed to making this telescope a reality. How do I get this? The brief outline of the talk, I will begin by describing sort of why did we build this thing? Why was it worth the many years of effort and the many dollars? The science drivers and the engineering choices that led to this being the telescope that NASA and the other agencies chose to build together. I'll talk about the technologies that were developed in order to enable JWST and to meet the extreme needs of having a large and very cold telescope in space. And then I'll tell some of the human stories that went into bringing the observatory into operation, the teamwork and the challenges, and how we went into deploying the system once it was in space. And look ahead to some of the future technologies, future space telescopes as informed by what we've learned from the JWST experience. But I want to go back and step, and we all build our science on the preceding work that's been done before. How many here remember when Hubble was launched? Hubble Space Telescope about 30 years ago, and there's a 10-year-old, and at least one in the audience, and that's how old I was when Hubble went up. So I do remember what happened after that, which is that the images from Hubble were not as had been hoped for. The system famously, infamously, suffered from spherical aberration. This was ultimately traced to errors in the polishing of the mirror on the ground. It was made precisely, but precisely wrong, due to in essence, the calibration machine. The way you measured the mirror was with a piece of ground equipment, and that piece of ground equipment was slightly misaligned. And so the mirror was made slightly wrong, and put in space, you get these blurry images. A lot of effort went into diagnosing through optical analyses, phase retrieval, and I'll come back to those methods because they're relevant for JWST, understanding the precise way it was measured and made wrong, and then developing systems that could be sent up and installed by astronauts on the telescope to correct the optical system and give the clear, crisp vision that Hubble is known for. And over the last 30 years, Hubble has become a tremendous success. It was 30 years ago, 1993, that the servicing happened to bring it into sharp focus. Shortly after that, Hubble was used for one of its most iconic observations, the Hubble Deep Field. This was to take the telescope and to stare at a blank field in space where nothing was seen and go deeper and integrate and see fainter light and to see, these thousands of galaxies going back to not that long after the Big Bang. But of course, scientists want to push further and want to see fainter signals and to better understand the first stars, the first galaxies, how the universe came into being and how the structure in the universe arose after the Big Bang. But there's a challenge in that, even with Hubble, as you want to go further and further back in time, looking at the distant universe. Not only does the light become fainter by virtue of distance, but because of cosmological redshift, the expansion of space over the last 13 billion years, the light is shifted out to longer wavelengths. What began its journey as visible photons from stars, billions of years ago, is now shifted into infrared photons. And there's a very simple relation of light from when the universe was, a tenth its current age has been stretched out to about 10 times longer wavelengths. So we need to go from the visible to the infrared to see those photons now. There's other scientific motivations for studying the infrared universe. This is an iconic image taken by Hubble of the M13 Eagle Nebula, often referred to as the Pillars of Creation. And in visible light, we see this beautiful nebulosity, this is dusty clouds, and stars are forming, planets are being born within this. Infrared light has greater penetrating power. And so if you go to longer wavelengths, you can begin to see through the dust. This clicker will work. There we go. And see the stars, the finer structure within the nebulosity, probe the way planets are forming and being born there. Of course, you see many more stars by penetrating through the clouds within the Milky Way. This is done going from the previous image was visible light. Now we're out at about 1.5 microns, maybe 3 times longer wavelength. And this is as far into the infrared as Hubble will go. So you want to go to longer wavelengths, we need something beyond Hubble. The scientific case for this has been made in a number of documents over the years. Really one of the iconic ones was this called the Dressler report from the mid-90s. In this report, the HST and Beyond report ultimately gathered input from the community and made 2 major recommendations from the scientific community to NASA on what they should do to set out the program to study the distant universe. The first recommendation, the HST, Hubble, should be operated beyond its currently scheduled termination date of 2005. Good plan there, and that has been done, and Hubble has been serviced by the astronauts and has been kept alive. The recommendation here says to keep it alive, an essential tool through the first decade of the next century. We're now in the 3rd decade of this century. Hubble is still going strong. We're aiming to keep it operational, hopefully to the end of this decade and perhaps beyond. The second recommendation they made was that NASA should develop a space observatory at least 4 meters in diameter, so larger than Hubble, optimized for studying the infrared from 1 to 5 microns at least, and extension to here from shorter to about 0.5 micron and longer to at least 20 microns would increase its center power. And this is the wavelength range in the infrared that JWST studies. Now, I promise these are the only equations in the talk, and they're very simple. The first is simply that the angular resolution, the fineness of detail you can see with a telescope, is proportional to the wavelength of light divided by the diameter of the telescope. So if you want to see the same fineness of detail that Hubble sees, but to do so at a longer wavelength, you need a larger telescope. It's that simple. You need to go to a bigger telescope to see the same details. Now, secondly, the flux, the emitted light from the telescope itself and from the background, the glow of background noise against which you make your measurement, goes as the 4th power of the temperature. And so for infrared light, where you're not just looking at the sky, but you're looking at the glow of heat, if you can make your telescope 10 times colder, well, you reduce the background not by 10, but by 10 to the 4. So you get a tremendous advantage in seeing faint signals if you can make your telescope very large and very cold. Well, that sounds simple, right? It's clear the design and manufacture will be very challenging. Yes, that's the story of the last 20 to 30 years to bring the system into reality. So why is it so challenging? Well, going back to Hubble again, these actually are both Hubble's telescope. And this is the Hubble Space Telescope, the optical system under construction within that. And this, the picture on the left, is the telescope that Hubble the man used 100 years ago to study the galaxies and work out the expansion of the universe. And these are optically very similar. The Hubble Space Telescope is, in a sense, a 100-year-old classical telescope optical design put in the space shuttle and launched into space. Very conservative technology. And optically, they're very similar. But this is as much as you can fit in a rocket. You're limited by the size of the rocket. This is, Hubble, to be clear, this is a large object. It's a school bus. It's a big thing. And to launch a bigger telescope than that, you need fundamentally a new approach, ultimately to fold up and pack the telescope inside the rocket and then unfurl it in space to launch something larger than you can fit into that rocket. And secondly, you need it to be cold. So the way JWST is designed, there's this big parasol umbrella sun shield to keep the light off. And you point that towards the sun, and the sunlight is blocked by this. And you have this very strong thermal gradient where it's quite hot on the side in the sunlight. And then over on the back side, it's extremely cold. It's 200 below zero, just a few tens of Kelvin above, a few tens of degrees above absolute zero. And that's what keeps the telescope so cold in the vacuum of space. And to do that, not only do you need it to be in space, but you need it to be far away from the Earth. So we send it out to this gravitational balance point, L2, a Lagrange point, where it'll move along and orbit around the sun, but always staying sort of opposite the sun in the sky. If you pardon imperial units for a minute, one of my colleagues refers to this as 1,000,000 miles to midnight. So if you think about the way you are in the middle of the night, pointing out into space, and keep it out there so that the sun shield is not just pointed at the sunlight, but the heat from the Earth, the heat from the moon, all that glare and heat is kept away from this extremely cold telescope. But this point, the gravitational balance point that lets this work, is 1.5 million kilometers away from here. So you need to build this large telescope and then send it out to that tremendous distance. So if we compare the telescopes, Hubble, the Spitzer Space Telescope, the previous infrared telescope that NASA operated in the early years of the 2000s, and JWST. And we can compare these in a number of metrics. The mirror diameter from 2 meters for JWST up to about 6 meters across the full thing. So it's clearly larger. If you look at the area, it's substantially, it's about a factor of more than 5 larger in area. But hold on now. Look at the mass, right? The telescope, in order to be moved so far away from the Earth, the most that rockets can carry was about 6 tons, which is half the mass of Hubble. And when it's folded up to get that far out, it's about 3/4 the size of Hubble. The most important thing to know about JWST is it is simultaneously larger and smaller than Hubble. So to do that, there's this tremendous engineering constraint to pack all this material, all this big optical system into a very small volume and a very small mass and send it out there. You can also compare to large ground-based telescopes, and that's even starker. The typical ground-based telescopes, 8-meter telescopes in Hawaii, in Chile, are 100 times more massive and 100 times higher volume with the dome and everything included. So you have 1% of the mass of a big ground-based telescope. This is a very lightweight system. Your mental model should be one of those racing bikes that had every gram shaved off of it. It's made of the lightest materials, the carbon fiber, the titanium. It is literally worth paying an engineer for a year to shave a few grams off the mass of the final system. So how do you do this in practice? There are 3 key technologies that were invented and invested in the early years of the project. And I'll go through each of those. But first I want to make the point that when this was happening, this technology development work, in the early 2003, 2004, and so on, I was a graduate student at Berkeley. I had nothing to do with the project at this point. Missions of this scale that take 2 decades to develop is a relay race. The new people come into projects, new opportunities come along, people retire, other people move and change roles. And so for the graduate students out there and young students, you can think about future space missions. This is an actual thing you can become a part of. If you follow the opportunities that came along, and I was able to follow some opportunities and become part of this. But to be very clear, I'm speaking on behalf of a huge team of people in the relay race of scientific research. And this is also true if you look at particle accelerators or gravitational waves or the development of telecommunication fibers. A huge, we all stand on the shoulders of the giants that went before us. So the first technology is very lightweight, very cold mirror systems. The requirement here was to be 10 times lighter than Hubble in mass. NASA funded industrial partners working with Ball Aerospace, with Kodak, and testing engineering models and evaluating these mirrors in order to achieve that. And ultimately, beryllium was selected as a material. Beryllium turns out to be a very lightweight metal, similar to aluminum, but lighter. But more than that, it's very stable at cold temperatures. It has a low coefficient of thermal expansion, so the mirrors are stable compared to when the temperatures change. It turns out, also compared to even ultra-stable glass, one of the benefits of beryllium is that you can make it very uniformly and very repeatably through a process called hot isostatic pressing. And so, again, drawing lines to nanotechnology research here, uniformity of process is very important. To be able to not just make large mirrors, but make a whole set of large mirrors that are very uniform, very similar in properties, can be tuned to work together as a system. And there's an industrial process that went along with that, working with industrial partners really across the US. There's a whole journey of how these pieces of hardware went from one facility to another in different teams that worked to fabricate them, to mill them, to polish them, to test them, to assemble the mechanisms on them, and get the telescope mirrors ready. Secondly, you need to be able to measure those mirrors and make them all work together as a system. We do this with something called wavefront sensing via phase retrieval. And the cartoon version here is that what you're doing is you take light and you focus the light down, and you want to take not just the picture of a star or a point source, a calibration light source, when the light is in focus, but also when it is before focus and after focus. And you can use the information content and the blurriness, the defocus of this to back out what the exact state is. And you can imagine, of course, those of you that wear glasses, you go to the doctor and they put different lenses in and you measure, what is this better or not with the lens in or not defocus. We're doing that modeling with computers to simulate the propagation of light and to fit a numerical model that gives us very precisely, nanometer precision, the state of light. And I'm showing on the bottom here, I'm cutting ahead to data from in flight. And if you could actually see a little more detail than is possible with the lights in this room, I'm blinking two images here, but you almost can't tell it. And that I'm showing real data measured in flight and the computer model fit to those same measurements. And they're basically indistinguishable. That's how precisely you can model the state of the light as it propagates from out of focus into focus and back out the other side. And from that, we were able to solve the inverse problem and get the measurements of the mirrors misaligned by a few atomic diameter, potentially, nanometers and below. And we use that then to send commands to move the mirrors back into the correct position. So each of those segments has on the back of it actuators that can move them in position, forward and backward and side to side, and rotate them around. There's also actuators that can actually bend the whole shape of the mirrors to adjust the focus of them individually. There's 7 of these actuators in each of the primary mirrors. There's 6 on the secondary mirror out at the front of the telescope. And the mechanism that operates in those, which was developed by a company, Ball Aerospace in Colorado, that's the primary contractor for the telescope system, is a really fascinating, amazing piece of technology. It is entirely mechanical. This is done with a gear train and transmissions and flexures to take a stepper motor, a little spinning motor drive, and at the other end of the mechanism, move it with a precision of 5 to 10 nanometers. Extremely precise. Now, why do that with a mechanical mechanism when it's often done on the ground? You do very precise things with piezos, with voice coils, with electronic mechanisms. Well, remember, again, this has to be cold. And this is a mechanical system. You can take the power off, and the just mechanical friction within the gear train holds it in place that precisely to within a few nanometers with 0 electricity applied. And of course, it's miniaturized and has to operate down to 15 Kelvin. It also has to be strong enough to hold against the vibrations and shock of launch. There was a tremendous amount of engineering, mechanical engineering, that went into designing these mechanisms in support of the optical control and moving the mirrors around. Well, how do you know that all these pieces will work together? You have to do an integrated demonstration. So NASA and Ball Aerospace built a scale model, a laboratory test bed version of JWST, and it's a 1:6 scale model, and it's in a laboratory, and you can control the mirrors the same way with those same flight actuators and measure the state and step through the process from going the 18 individual blurry, not focused light, focusing each of those so you have 18 sharply focused individual telescopes. Think of it as 18 telescopes we now have to bring together and align to act as one. The mirrors have to be aligned with the precision of as if they were all cut from one single physical piece of glass, one parabola, if you will, that they're all aligned to within nanometers. The third technology you need while you're doing that is the whole physical system has to be held together very stably and very lightweight, again, So there was a lot of work that went into developing composite materials. Again, the analogy with carbon fiber and bicycles is very exactly as a carbon fiber telescope. And so, but it is custom carbon fiber, optimized for space and optimized for extreme cold. There was a tremendous amount of work that went into having to characterize the material properties, understanding the properties of titanium and the carbon fiber and all these other things with the precision of a few parts per billion all the way down at 30 Kelvin. Tremendous amount of material science effort went into that. Again, repeatability, process control, so that you can make not just one, but many pieces of these. You can joint them together in clean rooms and bond them and end up with a structural system that meets the requirements of the mission. There's the picture on the left is a structural test article, not a part of the flight telescope, but was something that was built as a test piece to verify the process, to verify the technologies. And in fact, they had to develop new optical sensing methods, a kind of speckle interferometry. You need new sensing methods just in order to be able to measure that the physical stability of this thing met the requirements. So it was optical and mechanical engineering moving forward in sync for that. And then the picture on the lower right is the backplane structure behind the telescope. This is the center section that holds 12 of the 18 mirrors, and there's a case behind it for rigidity, and the science instruments are in there. And these were built and assembled over many years and tested and verified to have the requisite properties. So this telescope, which we've all seen pictures of, but if you pause and think about it, it's a really strange looking bird, right? It is not like any other telescope you've seen. It's this big tent on one side and is, ungainly out in the open, not in a tube. And the thing to take away from this is that specific set of design came from ultimately physical principles, that you need to have the sensitivity at the infrared, which means to have a large, cold, stable telescope. And in order to achieve that, there's this causal flow that goes, well, it has to be cold, and so it has to be far from the Earth, and it has to be lightweight. Well, it has to be very large, so it has to be deployable to unfold. And we have to unfold a sun shield to keep the heat and the light away. And so then you have this open design where it's exposed to space on one side, to the heat from the telescope cools out that way. And so the engineering design follows from the scientific principles, the scientific goals of the mission. Well, now we need to turn this from design. And this is about the stage at which I joined the project, I should say. The mission had been designed on principle, on paper. Now we need to make it a reality. Well, the first step is a lot of paperwork. So you have to have, you're coordinating a team, international, multiple space agencies, multiple industrial partners, multiple contractors. And so there's inevitably management and requirements and documents and flow down. The chart on the upper left is a flow chart showing which document sets other documents, and that information goes in more detail in a third document, and so forth and so on. And so in some sense, you don't get to begin building a spacecraft until you have a pile of documents and specifications and engineering design that is as tall as the spacecraft. And just an example on what one of these looks like, the thing on the bottom right, states about it will have a certain sensitivity as calculated in various ways, and it references these other documents of exactly how you do the calculation. You have to get this measurement at the end. And this is sort of how you coordinate from the scientists to the engineers, and then later you'll come back and validate and verify that the physical system you've built meets these requirements before it is ready to send into space. So now we're finally building the flight hardware. The mirrors had been in polishing for a while already. In fact, they were seen as one of the longest lead, most complex things, so they were started early. The individual primary mirror, secondary, the 18 primary segments, the secondary, and then other mirrors within the telescope itself that help focus the light down to the instruments. And all of those were completed by 2011. They then all came to NASA Goddard Space Flight Center in Maryland, where they were assembled together. This is a picture here of partway through that process with a robotic manipulator. This is a very large clean room, assembling the telescope there, putting each of these in precisely shimming it, connecting it, bonding it, testing those systems. A couple of years of work went into that. Once the telescope was fully assembled, we were able to set it up in the clean room and begin optical and mechanical testing of it. We were able to actuate the mirrors and show we could move them, sense their positions, work through the software control. There's a software engineering story as well as an optical and mechanical engineering story. And so here, this is the center of curvature tower here. and we would get up on that, and you can show lasers and interferometers and make measurements of the mirrors and verify the performance. At this point, in an ambient environment. We'll test it in vacuum later in the story. Now, in parallel, the science cameras were being built. These are the sensors that go behind the telescope and make the measurements of it. And I could give a whole story on each of these, a lot of optical technologies, detectors, microshutter arrays, spectrographs, a variety of things that went into that. I want to make the point that this is, again, an international contribution. The guider and one of the science instruments were contributed by Canada. Two of the science instruments were contributed by European consortiums, European Space Agency, and of course a lot of industrial and university partners, two major ones, University of Montreal and the University of Arizona, which I worked extremely closely with. They built the main camera, NIRCam, that we used for the sensing and alignment of the telescope, and so worked very closely with those folks. And all of these instruments came together by 10 years ago. They were done. Except they weren't done, because, of course, once it's done, you have to test it. And of course, you find in your testing that it's not quite right, and you have to make some adjustments, and then you take it apart and you test it again once you fixed it, and you iterate. And so 3 years of work. This is a picture of that whole assembly of all the instruments being craned into a vacuum test chamber at NASA Goddard, and put the lid on. You can see the lid over at the left-hand side, and it moves over and covers down, and you pump all the air out so it's in vacuum, and you cool it down, and you go through a whole series of mechanical and optical tests and software tests to verify the proper functionality of each of these systems. And as I said, you generally find that you have to iterate and try again until finally things are working as they should be. So then the telescope and the instruments together were taken for a ride and went by Air Force cargo plane from Washington, D.C. down to, this is arriving in Houston, Texas, going to NASA Johnson Space Flight Center. And the reason we were doing that was to take it to this facility, the Chamber A test facility at NASA Johnson. It's the biggest cryovacuum chamber in the world. It's about 17 meters across and 30 meters tall. And you can put the telescope in there, cool it down, test it out. Why is this facility there in Houston? That's why. It was built for the Apollo program to test lunar modules and Apollo landers with live astronauts inside for some of those tests. So we refurbished the facility and brought it up to modern standards, and we brought JWST there and set the telescope up inside this facility that you could put your house in and take your house down to about 20 Kelvin. And that's what we did with JWST. And in this test, there's a lot that goes into this, but briefly, it's a whole test program. You're not just testing in one test that you rely on. You test it, and this is true for many engineering and science projects. You test individual components, and then you test subsystems, then you test systems, and you test the functionality of the whole thing put together. You're doing that also so you can cross-check between different tests. But more than that, we wanted to do independent verification throughout all of this. Remember with Hubble, when it was launched into space, it had that focus error. These tests were not done fully with Hubble, and then they did one set of tests, and they trusted those were done right by the contractor. We divided things up, and sometimes we would divide the team in two, and each team does the data analysis without talking to each other. Or you say, NASA will do this analysis, and this industrial partner will do this analysis. Do you get the same answers? Good. Oh, you didn't. Let's do it again. And do this again, checking your work until we really build confidence. And when you could measure something two different ways with two different techniques, great, do that too. You want to test the processes and plans as well as the hardware. So we know we can operate it, we can know the measurements, the techniques, all the steps we will use in orbit. We tested those on the ground as well. And lastly, NASA has a general principle, which is test like you fly. And what that means is, don't just test for those requirements. Yes, do test the scientific requirements, the engineering requirements, but test that the whole thing actually works. Is it fit for purpose? Does it do what it is supposed to do, as well as checking all the checkbox from that giant flow of documents? But there's a problem. You can't actually test this system on the ground. It is too big. It bends under gravity. You can't fully simulate the stillness of space. That whole test chamber is vibrating because of vacuum pumps and tubes of liquid nitrogen that are 1/2 a meter across and all these things. So what in fact you have to do, this was a big challenge for the mission, is you're testing like you model. You build a computer model of how it should work on the ground in the messy environment of the ground, and you use the same computer model to show how it will work in space. And so the ground test is verifying that your integrated optical model, your thermal structural optical model, you've built the telescope, and you've built the telescope again in the computer. and you make sure that the computer model matches how it works on the ground, and the computer model also says it will work in space. Easier said than done. Tremendous amount of work that went into that, and again, independent verification, so you do that twice. You have different teams cross-checking their answers to verify that in the end the whole system will work. And this integrated modeling capability is incredibly important. You then take, meanwhile, the Sunshield, the spacecraft was under development. Those pieces came together, the spacecraft bus here assembled. We brought the telescope from Houston to Los Angeles, where the spacecraft bus was, and you can see the telescope, this telescope here, and then on the right, left rather, the folded up Sunshield and spacecraft bus. And those pieces were merged together, integrated, went through more deployment tests. 2019, everything was going smoothly, we were on track. What could go wrong? So that's how I spent the next 2 years, at home on a video call with my colleagues, in confinement, working on how do we pivot this giant engineering project to telework. How do you take and do by video call? How do you get the minimum amount of people on site to do the things with hardware while everyone else is at home? And doing it by video call with the kids and the cats and the dogs and all the human challenges of this period. I ran rehearsals for 2 years with people remote connected into the computers in the control center that none of us could go to. And so there's a whole set of human challenges that went into this of learning to operate these systems, learning to do the things we will do in mission control while the telescope was being finished, while we weren't sure when we would be able to get together and come together. A lot of human effort, frustrations, good days, bad days. This is a global story. We did eventually, in 21, vaccines came and more confidence in the system, and very carefully and cautiously we went back into the lab and went through continuing the rehearsal process. And in those rehearsals, we were both training the humans, the people in the process, but training the coordination of the teams of teams as we went through deployments, as we went through the entire telescope alignment, the commissioning process, as well, not just if things went good, but what if things go wrong? How do you deal with, how do we debug, practicing all of those processes that we would do with the telescope in space. And I want to pause here and on a personal note say, we were also practicing what to do so that no one person was a single point failure, that we would support each other for good or for bad reasons. And you know, I have more than once in my career lost a colleague in an untimely fashion in the middle of a project, and the rest of us had to figure out how to carry on. And we were here in Peter's memory, and again, science is a relay effort that we each do a piece of. And so we made sure that in commissioning, that people could carry on each other and support each other's jobs, and for good reasons as well as bad. One of my colleagues had a child right in the middle of commissioning, and so he went away and did that, and the rest of us carried on filling in those jobs. This brings us to Christmas Eve 2021, the telescope stacked on the pad at the European Space Agency's launch site in South America, my Christmas tree at home and the Christmas tree at the Mission Operations Center there. Strangest Christmas I've ever had, getting up at 2 a.m. to be in the office at 3 a.m., sitting at my console with my elf hat on, getting ready for launch.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
Beautiful, beautiful picture-perfect launch that day. We in the mission control, we were watching the signals, we were watching the same video, the beautiful sight of the telescope as it drifted away from the launch vehicle, unfolded a solar panel, and headed off into space. What did we have to do then over the next 3 months? I'm compressing a lot in this, I'm going to move a little bit faster, but broadly speaking, there were 3 main stages. The first, deploying, unfolding the spacecraft, aligning the mirrors, commissioning the telescope, bringing it to sharp focus, and then commissioning the science instruments. On that first day, the solar panel unfolded half an hour after launch, the high-gain antenna that we used to communicate with it. And the most important thing on launch day, after the launch itself, the first firing of the thrusters in space to steer the orbit to get it on the precise path out away from the Earth on a smooth trajectory towards that Lagrange point. Beautiful, amazing precision launch by European Space Agency, by Arianespace, one of their contributions. So we're on the way with plenty of extra fuel in the tank for many years of science. Superb launch, everything worked great out of the box. Very few engineering issues we were working with on launch day. The big scary part was the sun shield, the deployment of this giant structure, hundreds of mechanisms, 400 pulleys, hundreds of meters of cables pulling this thing out, sending commands from the Earth to let these mechanisms release and let the covers off. And then these mechanisms that telescope out on either side, pulling the sun shield out and then tensioning the layers so that it opens up in a fan, and each layer shields the one next to it from the heat of the sun and the Earth. Amazing work by Northrop Grumman. This was a very complicated piece, and in the end, it worked extremely well. The kind of technical problems that were encountered were by 3 or 4 hours later solved, and they went on to the next step, and over New Year's Eve and into New Year's Day, in the first few days of the year, the sun shield was deployed. Tremendous celebration at that point. We were through the hardest part of the deployments. Everyone was ecstatic, and again, credit to the folks that many people have put years of their lives into this. Of course, the telescope, we're just getting started now. We have this boom that unfolds to put the secondary mirror out in front. We were later able to measure that 8-meter motion, put the secondary in the right place within about a millimeter of precision. And then these two unfolding sets of 3 mirrors on the side of the telescope that came in. Now we have the full 18 mirrors, 6.5 meters across, assembled within the first 2 weeks of the mission. And at this point, we had to wait for it to cool down and then be able to operate the science camera. Basically, no surprises in this part. And then 2 days later, we had our first software fault that hit pause and everything until things were debugged. And that was part of the process in commissioning a telescope. You would make a few steps forward, you'd encounter an issue, you would take your time. We learned the discipline. We practiced in those rehearsals the discipline that it's more important to get it right than to get it fast, to work very carefully and methodically, deal with each issue, and then move on to the next step. We waited a while for the system to cool down in space. We're gathered in one of the offices of the control center, waiting to see those first photons that came down. And we received what I think of as the most beautiful mess. This is 18 different unfocused copies of a bunch of stars in a nearby galaxy that we looked at. But the key thing to see here is again, for all that this is a big, unfocused, blurry bunch of streaks, it's exactly consistent with what the computer models told us we should see for 18 separate unfocused telescopes. It was within the realm of expectation. We said, okay, we're in business, we're going to be able to measure these and align the telescope. So many stars is a little complicated to deal with. We went off and we pointed at a single bright, isolated star by itself. And we were able to say now, okay, we have 18 spots of light from the 18 mirrors. We begin the process of aligning those under computer control using the phase retrieval and using the computer commands that I said before. So we're going to zoom in on one of those segments. And the movies I'm going to show here, this is the real flight data as we were lining up the mirrors. It's a little hard here. I'm going to try turning off the lights in the room. Bear with me for a second here. Does that work? It does not turn off the lights at the front. Well, okay. I wish I could darker it more. There we go. Thank you. That's perfect. Very good. So the middle part will show the images seen with the telescope. The little animation in the upper corner is going to show the segments will light up when they're moved. So you began by moving those segments in, the 18 individual segments, bringing them together, and then lining them up in the pattern like the primary mirror. And you can see here, there's a variety of levels of astigmatism, blur. 2 of them are much more defocused than the others. And so we'll go through the process of defocusing them, switching to the other defocus, measuring, modeling in computers to derive the corrective motions that we send to those. And this process, this phase retrieval process, stretched over a few weeks. I'm not showing the full process here. Let's see, is this movie playing? There we go. And so as we went through the steps, you can see it sort of iterating and taking the different images. And after a few rounds of correction, they're all about the same level of defocus, all the same sharpness. We bring them back now into a sharp focus. We have 18 individually sharped telescopes, and we stack together the spots of light. iteratively, bringing them in, measuring, restacking, going through the process to bring together the 18 to act as one. And so this was one of the first images we took after that. This is what we released. I don't know if many of you saw the JWST blog at the time. We were releasing some of the images publicly to say this is the status of where they were. But we weren't showing all of them. This was the image that was taken right after that. And in this, you can see the bright star we were focusing on here. Some of these other things are actually a little bit curved, a little bit blurry, a little bit spiral. Those are the first resolved spiral galaxies seen with JWST, even in this early, not yet fully focused state. And now we go through another round, oops, too far, of focusing the telescope, applying sensing measurements. Okay, is this playing? There we go. With different levels of defocus, measuring, applying the corrections until the telescope, all those mirrors are lined up to within 5 to 10 nanometers, which is to say tens of atomic diameter, and we get this incredibly sharp, it's called diffraction limited point spread function. The modeling of the telescope, again, to go back to very quickly, the models proved to be extremely accurate and precise. The image on the left is a model we had from the ground-based testing. This is what we should get for the state of the mirrors in flight. And the one on the right is what we measured in flight. And there's some blurriness that's just a sensing noise from that. But if you look at the blue and the red are the high and the low regions of the mirrors, the slight as-built manufactured state of the mirrors. They line up exactly with the predictions. The telescope state in flight was exactly as it was predicted to be. But what we really want is the images. And this was the first deep images of the universe taken with the telescope right after we finished aligning it. We released one of the wavelengths, one color of light at the time, but it was in fact a full color image that we can see all these galaxies, this single bright star that we focused on, well, it's surrounded by galaxies. The universe is full of stars and galaxies that are now coming into view in the infrared universe. We focused not just to the main near-infrared camera, but to all those 4 science instruments that I showed before. This is, we pointed at a nearby galaxy and full of stars. And we can see sharply focused images in all 4 of those. Knowing we've aligned the telescope, we've focused it, we're now ready to start the science instrument commissioning. And that I could say a lot, but I'm not going to for the sake of time, say that each of these 4 cameras is its own right an incredibly complicated optical system with a bunch of different kinds of science, modes, measurements, for not just taking pictures, but for making spectroscopic measurements, for splitting light into different wavelengths to understand the composition of the galaxies, the stars, the planets. One of them, the near-infrared spectrograph, is one of the first infrared multi-object spectrographs sent into space. So it can get spectra of hundreds of galaxies at the same time to probe the very distant universe. Some of these instruments I'm using to help study nearby star-forming regions, nearby planets around newborn stars. A lot of effort went in over 2 months to test all of these modes, to calibrate, to update some software, to make sure things were working ready, to hand it off to the scientific community of the world. The scientific performance of the observatory is, I'm happy to say, truly outstanding. By sending it out so far from the Earth, not only do we get the sharp image quality of the telescope that was designed for, it's incredibly stable. We're here at a nanoscience institute in this building. The telescope is stable to nanometers just passively because it is so far from disturbances on the Earth. And so we measure it every 2 days. Well, after we lined up the mirrors, we didn't stop there. Every 2 days, we measure and check the state of the mirrors, and we correct it when needed, which turns out to be every couple of months. So it's extremely stable. Typically, it's about 5 nanometers per 48 hours. The instruments are all extremely sensitive, in fact, better than expected, due to attention to cleanliness and throughput. There's a whole team of people who worked as we built it and moved it around the ground and put it on a boat from Los Angeles to South America, a launch site in the jungle, which is not a clean place, to keep the mirrors clean so that you have as much light as possible get through them to the science instruments and to be measured. As I said, the pre-flight integrated modeling was incredibly precise and accurate. Now, you often hear JWST, it's working better than expected. And I want to put an asterisk on that and go one level finer in detail so you understand. It wasn't that we were it couldn't possibly work that well. We knew it could work that well, but in the models, we're always uncertain. How well do we trust our computer models? Well, you put in an uncertainty factor. You budget, the computer says some effect will be X. you say, well, let's budget it at 2x, right? Let's have some conservatism. Let's have some margin so that we know if the models are not quite right, we'll still meet the goal. Well, it turns out that many of those uncertainty factors were not needed, and the models were actually good enough, not in all cases, but in most cases. The models were right without putting in that padding, that uncertainty. And so the better than expected is really, there were fewer unknown unknowns than we thought there might be. There were fewer things that were not in the models. And that's really important for future missions. We can model these things extraordinarily well. It lets us design and verify on the ground and test systems that you cannot fully operate on the ground. I want to make the point that JWST, is in some sense a material science project as much as an optics project, right? And these things all support each other. And finally, the precise orbital control, this beautiful launch provided by our European colleagues as part of their contribution to the mission. And then the station keeping burns, we have to fire engines every few weeks to keep it where it's supposed to be in space. All works very well. There's fuel in the tank for more than 20 years of science. So we're in a very fortunate place because of that. I should say these are all written up in great detail in publications, the Astronomical Society of the Pacific, which is a scientific journal. But we make a point in this mission that everything has to be open access. So not just limited to the scientific community. If you want to go read the technical reports, you can do so. You can go to the Institute webpage, and there's a report, a commissioning summary report. My colleague Jane Rigby led, and I was privileged to co-lead, summarizing all of this in technical detail for the world, for the astronomical community that will use this as the broader public. None of this good performance is just accident or by luck. It's a result of careful work by engineers, by scientists, by attention to those performance margins, relentless attention to detail, and efforts over huge years by many teams. And even things like, oh, we got a better than expected launch. That was because they had, in fact, said we're going to set aside the best rocket and the best components and all of these things. Everyone went the extra few percent, put in 150% effort, if you will, to ensure that the success of this. And really, again, testament of long hours through the pandemic, meetings at 3 a.m. These photos show just a tiny fraction of the team of people that worked on this, that were able to contribute. 600 people in total worked on the commissioning of the observatory, gathered celebrating at the end in front of the Mission Control Center and Science Operations Facility that we had completed commissioning and were now ready to begin the voyage of discovery. Those first images that were released a year ago, July, the famous now view of the Carina Nebula with blue and these infrared wavelengths that were taking and showing invisible light. In essence, like an X-ray image, like an ultrasound, we're using computers to translate and make visible things that are not visible to our naked eye. People ask, is this really what it would look like? Well, that's a question as much about biology as it is about physics, right? These are the real wavelengths of light that we're translating into what our eyes are able to see. Studying the universe, the distant, most distant at the time, rapidly surpassed with this telescope, picture of the universe, galaxies, spectrum of an exoplanet. This was all done in just a handful of days, and we take this much data, more data than this, every week with the telescope. And that's studying the solar system, planets of the solar system, studying galaxies, star-forming regions, the birth of stars in nearby star-forming regions and the birth of planets around them, the death of stars. This is a star with clouds of material coming off that Peter Tuttle, professor here, was involved in studying. The spectra of really, as much as the pictures get attention, the spectra are what we get using for physics, for understanding the nature of these systems, the composition of the atmosphere, the composition of the stars, of the material, the dust and gas coming off of and flowing from stars into galaxies and back into new star-forming regions. Looking further into the distant universe, to the very edge of space and time, back to just a few 100 million years after the Big Bang, and seeing, in this case, galaxies that are distorted by the gravitational warping forces of the nearby galaxies between them and us. JWST is studying literally everything in the universe that is further away than the orbit of the moon. Things that are from Mars's orbit on out to as far as we can see across the universe. We are fortunate today, on a closing thought, to reap the rewards not just of the effort on this mission, but of advocacy and international partnership over many decades. In the US, we have a process, a master planning process, of every 10 years the community coming together and planning what are the top priority science questions, what are the things we should put our energy and resources to over the next 10 years. And this is advisory to NASA, the National Science Foundation, and other agencies. Europe has a similar partnering process. I was talking at lunch today with some of the early career researchers here about Australia's version of 5-year and 10-year master plans. So the recommendations to NASA, and these are not the only recommendations, but the Large Space Telescope System recommendations. Hubble, the Chandra X-ray Observatory, Spitzer. JWST was recommended in 2000, is now flying in the early 2020s. The next one in the system, the Nancy Grace Roman Space Telescope, will launch about 3 years from now, so very soon actually. And Roman is not a successor to Webb, but it's a partner. It is the wide field lens to the telephoto zoom of JWST. And just like your phone, you probably have the wide angle and the telephoto lens, and there's some things you do with each of those. We will have a Hubble-class telescope, but able to see 100 times more of the sky in a single shot. And that's under development and under construction right now at Goddard in the same clean room that we built JWST in. So stay tuned for that in 3 years. The recommendation that just came out for the 2020s is a technology development program leading towards what's now being referred to as the Habitable Worlds Observatory. And that's a bit of a fancy name for really a very challenging technical problem of trying to take a picture of an Earth-like planet around a sun-like star, something that might be 10 billion times fainter than the star that it's right next to. So you want to point an even bigger telescope than JWST at a bright star, block out the starlight and see the faint planet next to it, and ask, what is that world like? Is it an Earth? Is it a Venus? Is it a Mars? What is it like? What is out there in the universe? And so that we hope to bequeath that scientific journey further to the students of the future. And as I said, when JWST began, I was not part of the mission, and I was privileged to become part of that over the course of a few decades of career. And I'm hoping now that somewhere out there right now are the high school students, the elementary school students who will be doing science with missions still on the drawing board ahead in the 2030s, 40s, and beyond. Some lessons from JWST, and this is the wrapping up. We can launch, unfold, and finish building in space telescopes larger than fit within any rocket. JWST never existed on the ground in its fully configured, unfolded, aligned configuration. It physically could not do so on the ground. It couldn't support itself under its own weight on gravity, and the mirrors would bend, and it was too hot, and all these things. We built it for the first time fully in space, a million miles away. And the state of the art in modeling is very good, as I've said, and that means not only can we do things like JWST, we can do more ambitious missions through combining the power of modern computing with the power of modern optics and material science. Investment in those technologies early is essential, but it's also really, really hard. I mentioned with JWST, they put a lot of money in the mirrors early on and put that as a priority. Well, it turned out in the end, the sun shield was as big a driver of cost and schedule, and in the end, it was the sun shield that took the last several years to ready for launch. And so it's really hard to plan. And it's not unique to telescopes, but things like any what we call gigascale project. You're going to spend $1 billion on a high-speed train or a new piece of municipal infrastructure or a new set of airplanes. It's really hard to plan ahead. And this is just an ongoing challenge. How do you spend $1 billion wisely, managing, stewarding that as well as you can? These are generational missions. Mentoring is incredibly important. Teaching students, passing on the technical skills, passing on the team organization and management skills. I benefited tremendously from some key mentors at various points in my career that enabled me to be here. And it's a pleasure and a privilege to speak with students and early career researchers and to help pass on some of these things. There were a lot of young people that were involved in commissioning JWST. Just like I was able to learn from people that were part of the group that commissioned Hubble. And again, passing on, it's a baton, it's a relay race. Each set of experiments, not just opening new questions, but training people that will go on and answer those questions. Partnership, perseverance, and teamwork. Doing everything I was just referring to is not easy. It doesn't come cheap, it doesn't come fast. There's a lot of painful bureaucracy and budget meetings and discussions with funding agencies and uncomfortable things where some piece of technology isn't working as well as it should be, and you have to find more money to make it work. And it takes perseverance. There's good days as well as bad days. But in the end, if you stick with it, that teamwork and perseverance can deliver really transformative science. It's a pleasure again to speak on behalf of all the people, the thousands, the 20,000 people that worked to build this telescope, the 600 that worked to commission it and bring it to operations, and now the many thousands of scientists and students across the world that are doing science with JWST. Thank you very much for your time. It's a pleasure to be here, and thank you again to the Domachuk family.
Well, thanks, Marshall. That was great.
Thank you.
Before we go to the questions, a watch was found in the beginning, a gold pocket watch. If you lost a gold pocket watch, go and see Sergio. Where's Sergio? Oh,
Sorry, it's just
oh, it's here. So, okay, good. Good, so it's question time. Now, I'm sure not everybody will get the opportunity, but Marshall is available afterwards at the reception. So if we don't get to you, grab him afterwards. All right, good. Questions? Oh, yes.
Thank you. Thank you for the talk. Two quick questions. Firstly, just the data that's being received from the James Webb Telescope, it must be terabytes every day. So over the course of 10, 20, 30 years, you'll be having thousands, tens of thousands of terabytes of data. How do you store that? How do you process that? How do you get started with such a data-rich field? And the second question, I understand the focus on the visible light spectrum as being what is being looked at as part of the James Webb Telescope to get it out of the Earth's atmosphere so you can avoid the impact of the atmosphere. Would there be anything surprising, do you think, if we used technology other than the visible light spectrum on something like the James Webb Telescope to look at what's happening in the universe and in other wavelengths? So
I'll answer the second question first, and JWST actually is working at other wavelengths. It's working at longer wavelengths than the visible. So it's the near infrared from a wavelength of about half a micron. And so the very lowest wavelengths are visible light, and it goes out to about a factor of 20 longer, no, sorry, more than that, factor of 60 longer in wavelength. So it is an infrared telescope. There's a tremendous value in having what we call panchromatic, broad wavelength coverage. That's why Hubble in the visible and JWST in the infrared, the Chandra X-ray Observatory, other missions, there's a synergy between these. And it's really one of the things we want to do with the future is maintain what's called sort of the Great Observatories fleet, so that you have some capability at all the different wavelengths that you benefit from in space. Now, the data question, there's actually less data coming back than you might think, and that's limited by the fact that it's so far away. And actually, Australia has a big role in this. So NASA has what's called the Deep Space Network. These are 35-meter to 70-meter radio dishes spaced around the world that we use to talk with things like JWST, but also the Mars rovers, the solar system fleet. And there are 3 sites for that. One is Goldstone in California, the other is near Madrid, and the third is here in Canberra. And so the data, a third of the data that comes back from JWST, including some of the very first on launch day, flows from the spacecraft down to the big antennas at Canberra, and then flows from there to California, and then to Baltimore. Now, the data speed that we can bring back from that 1.5 million kilometers away is only 24 megabits. So this is like slow Wi-Fi speeds. We can pull down about 60 gigabytes a day. So it's data, but it is not big scale data. That's going to change with the Nancy Grace Roman Space Telescope. That will be moving into the era of big data. And Europe just launched one called Euclid, which is more data volume than JWST. It's big, but it is not big data compared to things like Google Maps or all the downward pointing weather satellites that are closer to Earth and can generate much more data. It's challenging to work with, but it's well within the capability of what you can do with standard laptops and computers and big servers.
Okay. Other questions? There's somebody behind you too, Kes, over there. Oh.
Thank you. Does L2 accumulate space debris, and is that a reason why JWST orbits around L2 rather than being at L2 itself?
So L2 is gravitationally not a stable point. There are other Lagrange points, L4 and L5, that do accumulate debris, not just from Earth, but Jupiter's Lagrange points have actually accumulated asteroids there, and there's a mission called Psyche Lucy rather, that's flying out to explore some of those that are caught in those points in Jupiter's orbit. We do worry about debris. We did get, one of the surprises in commissioning I didn't speak to was shortly after we finished lining up the mirror, we got a ding in one of the mirrors from a space rock, and we've been monitoring. We expected micrometeorite hits as something we would encounter and measure. No one likes getting the first ding in their new car, but it's going to happen. And it's a minor thing, but we're keeping an eye on those, and there are predictions when there are meteor showers. You can point the other way and stay out of that. The reason it doesn't orbit around L2 is actually just simply gravitation. It would take more effort to put it close in at that very center point. It can move in this big orbit, and that's sufficient. The other thing you want to do is you want to avoid putting it right at the Lagrange point, because then you would be in the shadow of the Earth, and it's solar powered. So simply ensuring you stay out of the shadow of the Earth and the shadow of the Moon at all times lets you run your solar powered spacecraft. There's a couple there.
My question is the power consumption, and especially for the transmitters. What kind of power do we think about that it comes all the way from there to Earth?
So the total power consumption of the spacecraft is about 1.5 kilowatts coming off the solar panels, and that's for everything. That's for computers and spacecraft systems and avionics and all the science instruments. The transmitter power, I don't know off the top of my head, but it's not much. It's watts, not kilowatts, and that's part of why from that distance you're receiving it on the ground with, again, a 35-meter dish is quite a big antenna to receive the very faint signal. Essentially a radio telescope. There's one there as well.
First, I've got to acknowledge what a wonderful job was done by 20,000 people. I sat, and one of the things that worried me was when they were unfolding those blasted parasol. I'm a bit of an engineer, and having, 400 single points of failure, it's not the way. You can't go forward like that, and you can't go forward with something that can't be serviced or replaced in situ. Wouldn't it make more sense than in the future? I mean, it's just a brilliant job, but wouldn't you be looking at a fleet of small telescopes that could work in unison together and you could have 10,000 of them up there around the Lagrange point, all communicating to each other, maybe all individually optimised at different wavelengths. And again, given the technology you've got now with coordinating and everything else, that could keep going for 100 years instead of, you're being shortchanged with 20 years on this thing.
So yeah, I would love to keep it. I mean, Hubble's going for 30 years, and I'd like to keep it going longer.
Yeah, but you can send people up there to do that.
Well, there's a bunch of different pieces in that question. I can only touch on them briefly. The management of the single point failures, there's a tremendous amount of work that went into that, as you might imagine, and testing on the ground and all of these things, and a lot of aerospace heritage. But absolutely, there were some scary things. There were some white knuckle moments getting through those big major structural deployments. At the same time, there's tremendous heritage as much as possible, and technology has been used on previous missions, even if extended and used in new ways in this. The servicing, I'm a huge believer in reusability and in servicing, not necessarily with astronauts, but also robotically. Robotics is getting very, very good. And so there's serious proposals to do in space, not just servicing, but in space robotic assembly of even bigger telescopes. And I've been involved in those studies. I think that's a very promising capability. Sending up lots of small telescopes is good, but in some sense, this is a fleet of small telescopes. This is 18 individual mirrors acting together as one. And to get that crisp, detailed image quality, they have to be lined up to within a small fraction of the wavelength of light. We don't yet have the ability to do that with free-flying interferometers that has been discussed. There's a study the European Space Agency is working on for an interferometer mission, also for exoplanet studies. So I think that's a very promising area for work in the future, but it is very difficult to do the formation flying to the fraction of a wavelength of light.
Okay. I think one more question.
Yeah.
Yes, okay, but then after that, I would like a question from one of our junior researchers here. I see, for example, here one on the first row. There may be others, but go ahead.
Just was wondering whether it's possible to use X-rays in the to X-ray out into space.
Yes, so one of the other telescopes that NASA operates is called the Chandra Observatory, and it is an X-ray telescope. Here we're not sending the X-rays out. We'd have to wait many years for them to travel the light years and come back. But we're receiving X-ray energy coming from space, from high energy phenomena like black holes and explosions of stars, supernovae. There's different technologies that go into X-ray optics. Normally you take a mirror and you send an X-ray at it, the X-ray just goes through the mirror rather than being reflected and focused. You have to build different kinds of systems for that. But X-rays and gamma rays are absolutely used in studying certain sets of phenomena. And there's other X-ray telescopes as well, operated by the Europeans. There's a Russian one as well. There's a new X-ray mission that the Japanese just launched maybe it's a month ago now. So that's another part of the study, generally for high energy phenomenon like black holes, as I was mentioning, things that go boom in the night.
Okay. One more question for a junior budding researcher. Any questions from them? All right. Oh, well, you're not a budding researcher, but... And sorry to all the others. I'm sorry, we're running out of time. As I mentioned, ask
Please,
Marshall afterwards.
Great. Very much happy to chat.
Does the heat shield perform a function of a solar panel?
The heat shield does not form the function of the solar panel. There's a separate solar panel that's right in front of part of the heat shield. The heat shield material is basically, if you have one of those, actually Martijn had one the other day, the silvery material you put in your car to keep the heat from going in the windshield. It's that kind of aluminized mylar, very similar to that. And that's just a light blocker and heat blocker. There's a separate solar panel that unfolds and sits in front of that.
All right, good, let's wrap up. Marshall, I have a few things for you. Two things. Well, the first thing you can't take home, but you are on our honors board.
Very good, thank you.
The second thing you can take home, thanks again.
Thank you so much, it's been an absolute pleasure. Much appreciated.